Okay, so let me start like I did last time with a reminder of where we are. We want a general solution of a differential equation like this, a second order linear homogeneous differential equation with constant coefficients. And our first step is to make this wonderful guess that seems to get us information every time. X equals e to the lambda t. When we plug it in, we get a characteristic polynomial. So after doing some algebra, we get this characteristic polynomial, a quadratic polynomial in lambda. And anytime you have a quadratic polynomial, there's the three possibilities, right? Either the parabola cuts through the axis in two locations, or in one location, or in no locations, right? So that leads to our three cases. So we got, I numbered them cases 1, 2, and 3. Case 1, two distinct real lambdas, lambda 1 and lambda 2. Case 2, only one lambda, or case 3, which was the parabola off the axis kind of picture, where there's no roots, no real roots. That picture was only showing you the possibilities if you only consider real numbers. In fact, there are always, for a quadratic polynomial, there are always roots. It's just they might be complex. So the no real roots case is actually the complex roots case. And when there are complex roots, they always arise as a complex conjugate pair. So you'll have lambda 1 and lambda 2, where lambda 1 is the complex conjugate of lambda 2, right? The relationship between lambda 1 and lambda 2 is that they have their imaginary part flipped in sign. Okay, and we already have handled case 1, so that's good. And we have already handled case 2, that's good. And we're still wondering about case 3. So that's where we are, and we will finish handling case 3 today. And that will complete our study of this exact type of differential equation, aside from applications and things like that. That will complete our mathematical study of this thing. So before we approach this, let me point out what principle was supposed to work for all cases. What led to all of these cases was this guess that x is e to the lambda t. If lambda satisfies this polynomial equation, then x equals e to the lambda t will be a solution to the differential equation. So no matter which case you're in, if you have a lambda, be it one of these two distinct lambdas or the only lambda or a complex lambda, no matter what case you're in, it is true that this is a solution to that differential equation. What we want is a way to write down the general solution, and we want a real solution. So we didn't say that before because it was kind of implied that when we, if x represents the displacement of a spring or the charge on some capacitor plates or something, in the end we want a real value for the solution. And we want one number, not two numbers, a real and imaginary part. We just want one number. Yeah, but no matter what, like even in the complex case, it's still true that e to the lambda 1 t, even if lambda 1 is actually alpha plus beta I, it's still true that e to the lambda 1 t is a solution. So this still is a solution. It's just we want the general solution. That's one thing we want. And we also want a real solution. This is not a real solution, right? Because of the I showing up here. If you work out what this is, it ends up having a non-zero imaginary part. So with these two things that we want, a real solution, and we want it to be the general solution. The general aspect we already know how to do. To get a general solution, we need not just one solution, but at least two linearly independent solutions. Then the general solution is any linear combination. So, for example, in case 1, we did get two linearly independent solutions. Since e to the lambda 1t and e to the lambda 2t are linearly independent functions, as we observed, any linear combination of them is going to be a solution. And when you write a linear combination with some unknown or free parameters as the coefficients, then that's your general solution. So you can use this to satisfy any initial condition that goes with this. So that's why I'm saying we are done with case 1, because this worked. We are done with case 2 not because this worked, but because something else worked, where you use e to the lambda t for one of your solutions, and then you use t e to the lambda t for the other one. And that seemed to work in case 2 specifically. So that was like a special case where we have something that works. In case 3, we still want something. And the reason I'm showing you this stuff again is that I just want to show you that this does work. This still works in case 3. Lambda 1 and lambda 2 are distinct in case 3. They're just complex, but they're distinct. And so e to lambda 1t and e to lambda 2t are linearly independent, and this does give you a general solution. But the problem is that this is a complex, not a real, general solution. And what we want in the end is a real solution.